Pozdravljeni v junijski epizodi astronomskega podcasta.
Temna stran Lune.
Oglašava se
Maruša?
in Dunja, ki vas bova ponovno popeljali v svet astronomije iz temne na svetlo stran Lune.
Hvala vsem, ki s svojimi prispevki podpirate podcast. Ponudite nam lahko namreč prispevek oziroma simbolično kavo na spletni strani ko-fi.com, poševnica temna stran Lune, in tako podprete najino delo.
Veseli bova med drugim tudi ocene in komentarjev. In sedaj lahko tudi tokrat začneva, ker naju čaka daljše potovanje. Se odpravljava v skrivnostni svet okultacij.
To se sliši zelo skrivnostno. Okultacije me spominjajo na nekaj mračnega ali pa okultnega. Dunja, o čem bova govorili?
Lej, nisi daleč, ker izhaja iz, torej beseda okultacija izhaja iz latinskega pridevnika occultus, kar pomeni skrit. In v astronomiji nekaj takih znanih zakriti tudi poznamo. Naprimer, ko Luna zakrije Sonce, torej sončev mrk. In recimo Luna ne zakrije samo Sonca, ne? Po noči se giblje tudi po nebu, zakrije še marsikatero zvezdo.
Ja, ampak zvezd pa ne zakriva samo Luna, lahko jo zakrivajo tudi asteroidi. In prav zato sva v Avstralijo poklicali ljubiteljskega astronoma Davea Heralda. In on se že več desetletij ukvarja z raziskovanjem asteroidov, raziskuje njihove orbite in pa oblike, in to ravno s pomočjo okultacij. Okultacije se zgodijo takrat, ko za trenutek asteroid zakrije oddaljeno zvezdo. In iz tega se lahko precej naučimo. In povedal nam je, kaj točno počne in kako se usklajuje z mrežo drugih astronomov po celem svetu.
Zato se sedaj zapeljimo na drugo stran sveta in prisluhnimo Daveu iz Avstralije.
Pa začnimo. Our guest today is Dave Herald, an Australian astronomer and an expert in occultations. He's the author of the widely acclaimed program Occult, that's been used to predict occultations, eclipses, and transits for more than 30 years. He's been maintaining the database of asteroid and lunar limb occultations for many years, and he received many awards for his work. The International Astronomical Union named the asteroid 3696 Herald in his honor for his astrometric observations of comets and his work on occultations by minor planets. The number of his cometary positions is the second highest in the world for an amateur astronomer in modern times, and his prompt and reliable attention to new comets discovered in the southern hemisphere has been invaluable. Dave, welcome to our podcast.
Oh, glad to join you. Pleasure to be involved.
Thank you. So we are going to talk about occultations and astrometric observations. So can you start by telling us what's an occultation and what's astrometry?
Thanks, Marisha. An occultation is the hiding of one object by another. The word comes, from understanding, from ancient history, from possibly Greek. Occult means to hide. And the use of occult in astronomy goes back a long way. In the last couple of hundred years, it's also been used in mystic areas to talk about the hidden things such as spirits and so forth. But that's a relatively recent use of the word. But in astronomy, it's one object hiding another object. So with the moon going through the sky, it goes in front of stars, and we refer those to be an occultation of the star by the moon. But you get some other phenomena which don't usually have the name but are still occultations. The most notable one is a solar eclipse, where the moon goes in front of the sun, and the moon occults the sun. But of course, it's got a very special appearance which comes with the solar eclipse, and it has its own set of names. Now, astrometry, which you asked about, that also got a very long history in astronomy. Goes back to the very early astronomers which were trying to identify or measure the location of stars. Astrometry is astronomy, metry, measurement. It's about measuring the positions of stars and how stars can move slowly amongst each other over periods of time. And astrometry is very important with you're dealing with things in the solar system to try to work out how that object is moving around the sun and being able to predict where it will be sometime in the future or where it was many years ago in the past.
What is the motivation to observe the asteroid occultations? So what can we learn about them, and why does it matter?
A very good question. Occultations by the asteroids, the first efforts were made, I think it was in the 1970s and certainly in the 1980s. Back then, not much was known about asteroids at all. Their diameters were quite speculative, and the aim of an occultation back in those days was to try to measure the diameters of asteroids. It was very difficult back then because the astrometry of asteroids was not very good. So we might think that the occultation might occur over Slovenia, whereas the actual path might occur over Australia. The accuracy was so bad. In more recent times, the accuracy of predictions has improved by a huge amount. So typically we know where an occultation will be visible within a few kilometres. Sometimes it's down to less than a kilometre. And we have two main objectives with observing occultations. One is still to measure the size and shape of an asteroid, and in the process occasionally discover a moon around the asteroid. And the other is to accurately measure the position of the asteroid and compare that position over long periods of time to measure a range of very subtle effects with the motions of asteroids, which I won't go into the detail of those subtle effects. It's worth noting that the type of precision that we can get with an occultation is far better than you can achieve with a normal astronomical telescope, such as the big telescopes on the Canary Islands. We can get positions of asteroids far more accurate than you can get with those big telescopes. In fact, with a recent mission, a space mission where the Americans had a mission called DART, where they projected a projectile into a moon of the asteroid Didymos to try to see how the impact would move the system. And since that event, a group of amateurs with small telescopes, the order of 20 centimetre diameter, and getting in their car and driving to remote locations where they expected to find the occultation, we've been able to measure the position of Didymos, the asteroid, to a position better than the normal astrometry before the event, better than radar observations, and better than the navigation instruments on the satellite, which was used to hit the projectile. And we measured the position of the asteroid to a precision of about 50 metres. which is a very small amount. And that's by a group of astronomers, amateur astronomers around the world with small telescopes. If you added up the cost of the equipment for the, say, 50 people who have done this, you'd be looking at a dollar figure of perhaps $100,000 or $200,000. And what can you buy for that in a professional observatory? Maybe a cup of tea.
Yeah, that's very, very impressive and very high achievement. So you mentioned how precisely can you can you measure the orbit of an asteroid? What about the details on their surfaces? You can measure or estimate the shape of an asteroid. How precisely can you measure the details of this on the surface?
We don't actually see the surface. We only see the edge of the asteroid. One of the interesting things with an occultation is the majority of events and the best situation is you can't see the asteroid. You need to have the asteroid fainter than the star because you're looking at the star disappearing. You don't need to see the asteroid. So the asteroid can be a kilometre diameter at a very faint brightness, the type of brightness where you need a 5-metre telescope to see it, to record an image. Well, if that asteroid passes in front of a star, you can see the star blink out and come back on again. And you don't need to see the asteroid, but you know when it blinks out the star, you know that the asteroid was exactly in front of the star. So if you know the position of the star, then you know the position of the asteroid. Now, in that process, we never actually see the asteroid, so we don't see what's on the surface. But if we have a group of people lined up across where the occultation occurs, then you get different paths of the star across the asteroid. And from that, we can determine the shape of the asteroid. And the typical average event, we would be measuring the size at a resolution of about 1 kilometre. And that's the same whether the asteroid is in the main belt between Mars and Jupiter, or if it's a trans-Neptune object out past Neptune and Pluto, we still have the same resolution. Possibly even better resolution out there, which is all a bit funny, but it has very high precision without needing very expensive equipment, just looking at the sky at the right time and seeing a star blink out and come back on again. By way of further explanation, the nature of the observation, you can think of, if you think of a star, it shines light, we see light coming from it, so it's shining light on the Earth. And if you put an asteroid in front of the star, the asteroid will create a shadow on the Earth. And that shadow is the exact same size and shape as the profile of the asteroid as seen from the star or from the Earth looking at the star. And the asteroid's moving, so the shadow moves across the Earth. And we measure the size and shape accurately by positioning our observers across that path. So each observer sees a different part of the shadow. And you can combine those observations and put together a very accurate shape of the asteroid.
How many observers do you usually need, or how many are there typically for a typical occultation?
First of all, around the world, we have about 450 active observers. they're scattered around the world. The main regions, America, Europe, Japan, and Australia. And generally, observations are within those regions, but occasionally you get an occultation go across regions. For example, we had one earlier this year where it was observed in Europe and Japan, and from that observation, a satellite of that asteroid was discovered. The observer in Europe recorded one body, and the observer in Japan recorded another. As to how many people we have see one occultation event, it's very variable. The majority of events, it's usually people at home by themselves, and they get a single call across the asteroid. If the asteroid's very large, you don't get a very good position of the asteroid. If the asteroid is small, you're measuring the position to a fraction or a half of the diameter of the asteroid. If it's a larger asteroid, then we will try to have people spread across the path. We have had some events where the number of people have been up to about 100. There was a recent spectacular event in Europe on December the 12th last year, where an asteroid passed in front of the star Betelgeuse in Orion. And that had over 70 observers doing that. And that was an interesting occultation because the asteroid was smaller than the star's apparent diameter. So you have the asteroid going in front of the star, but you have you have parts of the star appearing on either side of the asteroid. A bit like an annular eclipse, except the asteroid was not round.
So we are talking about occultations, but it seems to me that these chance alignments between asteroids and distant stars this must be very low chance. So how do you predict such events? I think you are the best person to answer this. And then also, are there any online tables for any future occultations of the brightest stars? And also, how many occultations are there typically in a year, for example?
Firstly, the prediction process. We use a very accurate star catalogue, the Gaia catalogue, and usually we go down to magnitude 16 stars, which is fairly faint, but it's accessible by the larger amateur telescopes. And we have the orbits of asteroids are known, and the process is to compute the position of the asteroid on a regular basis, check it against the star catalogues, and when they're sufficiently close, have a detailed prediction and find the occultations. How many do we find? Well, firstly, a typical search for asteroids down to, say, 5 kilometres diameter, there would be 5 or 10,000 asteroids, a fair number of asteroids. Now, then each asteroid moving through the sky, I forget the exact numbers, but you could expect for a typical asteroid, it will pass in front of a star as seen from somewhere on the Earth once every 3 or 4 days on average, because there's a lot of stars in the sky. And the Earth's quite large compared to the size of the asteroid. Now, you can do your maths about that, and in theory, there can be a very large number of occultations. For the keen observers with largish telescopes, well, the list of potential occultations I could observe here with a 16-inch telescope is 3 or 4 per night. Sometimes it's more than that. The success rate with those is not so great because the probability for some of them is quite low. But there's some nights where I've successfully observed 3 occultations. And that's a few people around the world do that. 2 occultations a night is not uncommon at all. But you can have periods where there's none. And at the moment in Australia, we're going through a low number of occultations being predicted each night. It's just geometry. One of the factors in observing or being able to record occultations is you don't want them too close to the sun because you won't be able to see them in twilight. You need to have the asteroid no brighter than the star, preferably fainter. And you also need to have the duration of the shadow reasonably long. When I say reasonably long, at least half a second. The typical event we observe, the duration of the occultation would be 5 seconds or less. It's quite a short event, but we record things at 0.02 second type resolution. Sometimes we get events, the occultation can last well over a minute. And in theory, you can have an occultation which lasts a very long time. If the asteroid is near its, what we call its stationary point, where the asteroid motion in the sky goes from being east-west to west-east, then at some point it has very slow motion in the sky. And it, in principle, the shadow as crossing the Earth can take more than 24 hours to cross the Earth. And it can come into the Earth in one direction, turn directions and go back off the Earth in the direction it came. Very rare events. We haven't actually observed one quite at that point, but we've certainly, the typical time it takes for a shadow to cross the Earth is about 15, 20 minutes. But we do observe events where the shadow takes 1 or 2 hours to cross the Earth. So a variable factor, it's all tied up with how fast the asteroid moves, and in the sky, the rate that it moves varies depending on where it is in the sky.
Are there any online tables of the future predictions, or do you have to go and use your code occult, or is because you have to enter your own location, or do you are there any tables with predictions?
We have there's online pages. There's a package or a site called Occult Watcher Cloud.
Mm-hmm.
So if you do a search for Occult Watcher Cloud, or OWC,
Mm-hmm.
that is a site which gives comprehensive predictions, and you can specify your home location where you observe from, and that will filter out and give you a list of occultations which will occur near you.
It's very convenient.
And there's some other tools of that nature.
That's
if
very
you
convenient.
if you do an online search for OWC or
Mm-hmm.
Occult Watcher, you will find something. If you do a search for asteroid occultations, you should be able to come across the group in your region. There's active groups in Europe, Japan, Australasia, and North America, and also South America. There's a small group there.
Mm-hmm.
So it's I can't give you the web addresses there, but it's because it's there's so many potential events, because the base predictions have to be done for the whole world, and then you filter them to your region.
Yeah, yeah.
Also, we have a process to update the predictions as new orbits become available, which could be every few weeks. So our aim is to have the most accurate prediction available. And these days, the predictions are pretty good.
My question here is, who can participate in the observations of occultations, and what equipment do you need? I believe that if you are recording such things that are transient but are, you will have probably to have a very, something that records the time very accurately. And what other equipment do you need? Probably for recording some camera. And another question that is a side question to that is, what is your equipment? I believe that some of the listeners probably are also amateur astronomers, and they want to know what kind of equipment do they need to take part of on that observations.
Okay, on the equipment side, well, firstly, generally, if somebody has a telescope of almost any size, you can participate. But the smaller the telescope, the fewer events you can see. But we do have people in mobile setups who have been very successful with telescopes made up with half a binocular. So 40 centimetre diameter, and put a camera on it and set it up in the field somewhere, and they can record an occultation of a bright star. And we've had some very successful events with that. On the other hand, you have telescopes, 20 centimetre telescope, which is a very popular amateur size telescope. You can do a lot of observations with that, and that's the most common telescope size that we have. And I have a 40 centimetre telescope, and we have a few people with that size telescope, and you can observe even more. Equipment. Well, obviously you need a telescope to be able to record the star. The most important factor is accurate time. It is the single most critical feature. In the occultation community, we have several ways of achieving that. We have special equipment which makes use of GPS satellites and a particular signal that comes out of the GPS satellites, which gives time accurate to about a nanosecond. The type of time that mobile phones get from a GPS satellite is of much, much lower precision. And there are various devices that you can get which access those signals, and you can use to get the time recording. One of the time sources which is unreliable is NTP time, which you get on a computer, unless the computer is set up on a very dedicated network. NTP time has got problems. Now, what was the next part of your question? Oh, the other equipment you need is to be able to record it. Before 2000, it was all visual, and visual observations have a lot of problems. About 2000, low light video cameras became available, and the typical video camera is much smaller than the handheld video cameras, and we have devices which take the video stream from the camera, which is 25 frames a second for European and Australian cameras, 30 frames a second for America and Japan. And we can timestamp each frame of the video camera with video insertion technologies. More recently, people have started using more standard CCD cameras, You need a camera which can take images at a high frame rate, and people are getting down at 100 images per second. And that gives you very high resolution if you've got the star brightness. Now, of all those, the cost factors, the telescope would be the largest cost factor. The camera, if you've got a CCD type camera, would be the next most costly factor. And the time part of the equipment is the third component. And that's a significant cost, but it's not a huge cost. Some hundreds of dollars, not tens of dollars. But beyond that, if you have that gear, you can participate. All you've got to do is point the telescope at a star at the right time and record it.
And to know the right time, you will have to use the software. That's the occult software that you developed,
generate
right?
we generate predictions which you can be specific for your location. And what some people do, and it's fairly common in the United States, but we have some people in Australia, they will have several portable telescopes, maybe half a dozen telescopes. And you have a predicted path, and they'll get in their car and drive to it, and they'll get out the first station and set up the telescope and the recording equipment. And at the right time, they'll know where a certain bright star will be at a certain time at the same location where the star to be occulted will be at the right time. So they have to set the telescope set up stationary and have the recorder set to start recording at the right time. Then they'll drive a few kilometres down the road and set up another one. And they'll do that for an array of telescopes. And they'll set up the last one 10 or 15 minutes before the event. The event occurs and they drive back down, picking up their telescopes, and then go home and analyse the recordings. And all of this is on country roads. They tend to put them behind trees so you don't see them from the road. And I think we've only ever had one instance around the world where a telescope system has disappeared. And some of the telescopes that people set up are quite large. We've had people with 30 centimetre diameter telescopes, which they set up that way, and they're designed to be portable, designed to be able to go in luggage on planes. It just folds up, a mounting which supports the mirror with some truss arrangements to support the secondary mirror, and just folds down into a small box, very portable. And you don't need any drives. You just need to be able to point it at the right place when you set it up so that at the right time, the star is in the field.
So we have been talking about measurements, observations, but so let's go back to asteroids themselves. How many asteroids have their shape determined so far?
I'd have to check my database, but the occultations, we have good shape measurements for many, many hundreds of asteroids. But one of the issues here is that we only get a profile measurement, which is just a single profile, which doesn't give you the three-dimensional shape. And this is where there's another area of amateur activity becomes involved. There's a group of amateurs who make dedicated light curve measurements of asteroids, very accurate measurements, and they need to do this for the asteroid being in different parts of its orbit. And you get the light curve varies. Well, you get a light curve. The brightness of the asteroid changes as it rotates because generally the asteroid is not spherical. And if it is elliptic, then on one orientation will be brighter than in another orientation. So you get the reflected light from the asteroid varies in brightness, not by a large amount, but by an amount. And the amount that it varies depends on which part of the asteroid you're seeing, which depends upon how the axis of rotation of the asteroid appears in different parts of the sky. So you can be at one part of the orbit and you have very little light variation. In another part of the orbit, they can get quite large light variation. And there's a group which worked out the mathematics to bring these light curves together and do a model of the shape of the asteroid. And they can generate quite a reasonable, low resolution model of the shape of the asteroid. But they've got no idea what the size is. And for most asteroids, there are two solutions, not one, but two solutions. There's an ambiguity in the mathematics. The occultations, when we observe an occultation, we can go to the shape model size, shape model source, predict the orientation of the shape model at the time of the occultation, and fit our occultation observations against that shape model. And that will give us the size of the asteroid. And it can also give us the location of the center of mass of the asteroid. And it's an iterative process because the people that do the shape modeling also take advantage of the occultation observations to improve their shape models. So our observations get fed into the shape modeling. The shape modelers get the shape and the occultations generate the size.
What about the other way around? So we've been discussing what can we learn about the asteroids, but what about stars? What can we learn about stars from such occultations?
The learning of stars is fairly limited. The most common thing we find is discover that the star is not a single star, but there's a very close companion star. And for those we see typically the light, instead of just dropping in an instant, it will drop to half brightness and then drop to the low brightness. Occasionally you'll get the star dropping in brightness and rising, and then another drop in brightness and rising, all due to the star being a double star. And with one exception, we've discovered, I think it's about 200 double stars, none of which are previously known. They're all discoveries, and none of them are identified as double stars in the Gaia catalogue. So we're actually making measurements at a level of resolution which other techniques generally cannot achieve. When you have large diameter stars, you can derive the diameter of the star, but that becomes complicated because the stars with a large diameter are usually red-coloured stars. They're relatively cool to give the large diameter, and those stars have what's called limb darkening, where the star appears darker at the limb than in the centre of the star. So the light curve you get is complicated. It's also complicated because the shape of the asteroid is probably unknown, and analysing the light curve is quite difficult. So in that sense, you don't get any precise details about the stars. Occasionally we get an observation where it's being very clear that the position of the star in the Gaia catalogue is wrong, and by many milliarc seconds wrong. Doesn't happen often, but we have had it happen. And we've had it happen with one of our more critical observations, where for the first observation, the star position was wrong. And when we updated the predictions for the following ones based on that event, the predictions for the subsequent events were wrong because we'd updated it using the wrong position for the star.
What about the moon? The moon, the angular size of the moon is large in the sky, and I guess occultations are more common. What can you learn about the moon through such events?
Occultations of the moon were very popular between, well, the first occultations were observed in Paris in the early 1700s, I think it was, when the motion of the moon was very poorly known. And occultations were used in the 1700s, 1800s and 1900s to improve our knowledge of the motion of the moon, which is quite a challenge to actually predict the motion of the moon. There's an awful lot of complications. Around about 1910, 1915, there was a great improvement in the accuracy of predicting the moon, position of the moon. In the analysis that led up to that, the people involved started suspecting that the rotation of the Earth wasn't uniform. And as a result of that, they wanted to use the moon as a reliable long-term time source and see if the rotation of the Earth was uniform. So observing occultations was strongly promoted from about 1920 onwards, and that continued up until the 1990s. But it was a fundamental measurement which led to the realization that the Earth's rotation is not uniform, that it's generally been slowing down, and led to the, there was atomic time and coordinated universal time, all came out of that type of observation. So fairly fundamental to a lot of what we do today.
Yes.
Apart from that, they were used a lot to try to measure the shape of the moon, the edge of the moon, which was not well known. And a lunar occultation, you can measure things with an accuracy of a number of meters in the right circumstances. But these days, with the spacecraft that have gone around the moon's topography has been well mapped. And these days, there is very little to be learnt from observing lunar occultations, except for the occasional discovery of a double star.
And now we go to the comets. So you're a very avid observer of comets, and you have built your own home observatory in your backyard. And can you tell us a little bit about your observatory? And also, do you have any tips for comet observations? Now, it's also visible from Slovenia. It's comet Pons Brooks. Do you have any tips, or what's your observing strategy?
My observatory, I have a 40-centimetre telescope in an observatory I built. It's effectively a garden shed with a roof that rolls off. Every garden shed should have a roof that rolls off. And it's convenient because I can have it permanently set up, and I can, if I decide, oh, there's an event on tonight and I've forgotten about it, I was having too much wine or food to eat, I better rush out and observe it. I can get it on, open up the observatory, get it onto the target star and record it in less than 5 minutes. Huge advantage of having a permanently mounted telescope.
Yes.
If you've just got a telescope which you've got to set up, well, it'll take you half an hour to set it up, and you need to have special events to do that. Comets used to be a very major activity in what I did, not so much these days.
Mm-hmm.
The history of it, my involvement with comets, goes back to the 1970s, where there was a gentleman by the name of Bill Bradfield in Adelaide, who's become one of the most prolific discoverer of comets ever. He doesn't have the most, but it's a very large number. And the issue with comets, the typical visual discovery of a comet, the comet was usually fairly close to the sun. So it was picked up early evening after sunset or morning in the hour or two before sunrise. And that created challenges for being able to get the position of the comet so that you could measure the orbit. And back in those days, the accuracy of star positions was quite low in relative terms. And the basic principle is you needed positions of the comet over 3 days. Now, at that time in the southern hemisphere, and Bill Bradfield's discoveries were all very, very far south. When they were discovered, they weren't visible in the northern hemisphere. And in the southern hemisphere, there were effectively 3 people that could do the astrometry. There was a person in New Zealand, myself, somebody in Perth Observatory, Western Australia, and for a number of years, somebody in South Africa. And there was a bit of a challenge between the 3 or 4 of us of who could get the third position so that the orbit could get established. So throughout the 1970s and early 80s, Bill Bradfield was discovering lots of comets, and we were going out to measure the positions as best we could so that an orbit could be established. And by doing that, we ensured that all of Bill's comets are Comet Bradfield. It's not Comet Bradfield Fred, Comet Bradfield Hubble. He's got his name as a sole name, as a sole discoverer for every one of his comets, because we were able to get the observations to determine the orbit before anyone else could discover it. And the challenges to do that were quite interesting. I remember on one event, the comet was going into the sun. To measure the position of the comet, for it to get above the horizon, but the twilight not being bright enough to block it out, I got the required astrometry when the comet was at 2 degrees altitude.
Wow.
Which is very low, and you get interesting effects with refraction at that altitude about how it's very complicated measurement to be made. So I did that over many years. My main interest was to measure the positions of comets, and that's challenging because you don't actually see the nucleus of the comet, the lump of rock that's there. What you see is reflections from the gas and dust that surround the nucleus of the comet. And that's not necessarily where the rock is. The rock can be displaced from the center of that. So I did that for a long period of time. But in the last 15, 20 years, I suppose, the asteroidal occultations has taken over my life.
You were talking about moons, and then I'll ask you how many are known at all, because I don't think it's well known that asteroids have moons. It's like a general question.
Asteroids, currently there are several hundred asteroids, but only a small number of hundreds of asteroids that are known to have moons. When occultations of asteroids were first being observed back in the 1970s, we had a number of observations made visually where the observers claimed to they see the occultation event and then they see a second occultation event. And they thought, oh, there's a moon. That's the only explanation. Well, at that time, professional astronomers said, don't be stupid. Asteroids can't have moons. And with the number, we've got up to about half a dozen asteroids where people say, well, I think I saw a moon. They did some investigations with very large telescopes and the Hubble Space Telescope. And of these asteroids said to have moons, they didn't find any.
Mhm.
So no more moons. Then a spacecraft went near an asteroid, I forget which asteroid, and it had a moon.
Mhm.
So, asteroids can have moons. And moons have been regularly discovered, supposedly using the light curve variations and looking at shapes, the light curve shape for eclipses and occultations of the moon and the main body. In recent times, we've been in the occultation community looking at smaller asteroids, relatively small asteroids, less than 10 kilometres diameter. And we've been successful with that only in the last 2 or 3 years. And we've been finding several instances of 2 occultation events. We've got 2 instances where we have several instances where people see 2 drops in the light curve.
Mhm.
The first one, which was a substantial discovery done by 2 amateur astronomers near Sydney in Australia. They both had 2 occultation events, 2 dips in the light curve. They were separated by 6 or 8 kilometres. And the only the explanations are the asteroid is either a double system or it might be a double star, but you can do some analysis to exclude the double star. And subsequently, that was confirmed with another similar observation. And after that, it was confirmed with analysis of the Gaia astrometry of asteroids. They were able to establish a wobble in the orbit of the asteroid due to its motion in the Gaia data. We have a couple of situations where each observer just records a single occultation event, but when you bring them together, you find that you have the occultation chords aren't aligned. They're displaced sideways and in time. And they're the only the explanations are possibly a double star, you've got to exclude that, or an asteroid with 2 components. And all in all, we now have 6 asteroids with satellites discovered by our occultation technique, and we expect to be finding them hopefully a couple a year.
Wow,
It's,
it's a lot. It's a
yeah.
lot. Yeah.
But what we're finding is satellites around small asteroids. The early discoveries were satellites around larger asteroids at a long distance from the asteroid.
Mhm.
The ones we're finding, the asteroid diameter is typically 4 to 10 kilometres, and the separation to the satellite 10 to 30 kilometres.
Oh, wow, that's very close.
So
And what's the,
quite
I don't know,
small.
mass ratio or maybe size ratio? Are they equal? No, they're not equal size because it's a satellite. So satellite must be smaller.
We have them from the components being similar in size to the satellite being much smaller than the main body.
Mhm.
But our statistical sample is small, so
Yeah.
it's still a matter of discovery.
Dave, thank you for joining us today and taking us to this wonderful world of occultations. And we hope that we inspired some of the members in our audience to take their own telescopes, go out and go and try to observe these occultations.
Okay, thank you, Marisha.
V tokratni rubriki o astronomskih novicah se bova na začetku zaustavili na dveh takih bolj šolskih novicah. In sicer Fakulteta za naravoslovje Univerze v Novi Gorici je konec februarja v sodelovanju z Zavodom Kozmolab, pri katerem sodelujeva tudi medve, razpisala natečaj Gočile, zvezdnate ptice južnega neba. In ta natečaj je bil namenjen dijakom in dijakinjam. Naloga tekmovalcev in tekmovalk je bila, da s teleskopom Gočile opazujejo vsaj dva nebesna objekta, neko galaksijo, kopico, meglico ali pa neko posebno zvezdo, in to v enem ali več ptičjih ozvezdjih južnega neba. To so pa pav, rajska ptica, krokar in feniks. Opazovanje sicer ni bilo vse, torej celoten projekt, ampak je skupina dijakov morala objekte in ozvezdja tudi povezati v zgodbo ali pesem, ki so jo lahko še dodatno obogatili z grafičnimi elementi. Izmed 5 skupin, ki so se prijavili in uspešno opazovali objekte v prvi polovici aprila, je komisija ocenila, da so bili izdelki sicer zanimivi in izvirni in podelila ne samo prvo nagrado, ampak tudi drugo nagrado. Torej, prvo mesto so osvojile dijakinje gimnazije Poljane, to so Lili Ačeto-Vranac, Julija Marolt in Lena Štelcar pod mentorstvom Roka Kovača, in sicer z izdelkom Utrinek, kam si izginil. Nagrada tega natečaja, ki jo bodo potem prejele konec avgusta, je teleskop tipa Dobson. In komisijo je pa prepričala tudi mitološka zgodba o Sončevi poti, ki sta jo napisali Mojca in Meta Grudnik, zato se je komisija odločila tudi za dodatno, torej drugo mesto in seveda ustrezno nagrado. Čestitke torej vsem sodelujočim in vse zgodbe in izdelke, ki so jih dijaki in dijakinje pripravili, si lahko ogledate tako na portalu V vesolje kot na spletni strani Zavoda Kozmolab in res priporočam, saj so zelo zanimivi in so se res zelo, zelo potrudili. Za vse torej radovedne najdete povezave v zapiskih. In še druga, bolj šolska novica, je pa o projektu Sončevih sledi v pločevinki. To je bil mednarodni eksperiment Solarography-Cans, pri katerem so sodelovale šolske skupine iz različnih držav Sredozemlja. Sredozemlja in tudi dlje. Solarna pločevinka je v resnici neke vrste majhen domači fotoaparat z luknjico, torej pločevinka z luknjico, ki omogoča, da na fotografski papir, ki je nameščen v notranjosti pločevinke, zajamemo sled sonca po nebu skozi čas. In taki sliki pravimo potem solarografija. Namen takega poskusa, tega mednarodnega poskusa, je bil opazovanje sprememb sledi sonca na nebu, in to iz različnih držav. Na ta način naj bi se opazilo, da je premikanje sonca po nebu odvisno od geografskega položaja opazovalca. Organizatorji tega eksperimenta so tudi organizatorji astronomskega festivala Vesolje v vseh čutilih na sledi časa, ki bo letos potekal od 7. do 9. junija v kraju Castellaro Laguzelo v Italiji. In kot so nam povedali in so že začeli z nalaganjem torej vseh teh raznih slik, ki prihajajo z različnih držav, na spletno stran festivala, in lahko jo pregledate tudi v zapiskih te epizode. Poleg slovenskih šol so sodelovale tudi šole oziroma šolske skupine iz Italije, Nemčije, Grčije, Turčije, Libanona in Irana. Zaradi velikega zanimanja so organizatorji med drugim tudi odločili, da bodo še naprej zbirali rezultate poskusov in sproti posodabljali spletno stran. Tako da sodelujoče slovenske šole lahko svoj rezultat še vedno pošljejo na naslov info@cosmolab.si. In seveda čestitke vsem šolam, ker so bili vaši izdelki res odlični.
V tretji novici pa potujemo na Mars oziroma na njegovi luni Phobos in Deimos. Mars ima namreč 2 luni in sta zelo posebni, nista okrogli tako kot naša luna, ampak sta bolj krompiraste oblike in sta zelo, zelo majhni v primerjavi z Marsom. Imata samo 15 oziroma 25 km in pa tudi zelo majhno relativno gostoto. Posuta sta s kraterji in glede na to, da sta zelo posebni, so se astronomi že dolgo sprašujejo, kako sta nastali. In obstajata dve glavni teoriji. Prva je, da sta to asteroida, ki sta se ujela v Marsovo orbito in na to sklepajo zato, ker sta njuna spektra zelo podobna spektrum asteroidov v asteroidnem pasu v družini trojanskih asteroidov, ki so povezani z Jupitrom. Ampak ta teorija ne pojasni nekaterih specifičnih lastnosti njunih orbit okrog Marsa. Po drugi strani je pa teorija, ki govori, da bi lahko ti luni nastali iz razbitin. Ko bi se recimo neko večje telo zaletelo v Mars, bi nastale razbitine in potem bi ti luni nastali iz teh razbitin. Ampak po drugi strani pa ta teorija razloži njuni orbite okrog Marsa, ampak ne razloži tudi njihove kemijske sestave. Tako da vsaka teorija ima eno dobro stvar pa eno slabo, to, kar se lahko da razložiti. Sta pa tudi ti dve luni posebni zato, ker iz spektrov sklepajo, da sta polni organskih spojin, oglika, silikatov, lahko bi po notranjosti skrivali celo vodni led. No in pred kratkim je pa objavljen članek, kjer so raziskovali nekatere lastnosti Phobosa, njegove fotometrične lastnosti, iz posnetkov, ki jih je naredil Mars Express. In ugotovili so, da je njegova površina zelo temna, njegov albedo je namreč le 7%, torej odbijala je 7% svetlobe. Vedo tudi, da je njegova površinska sestava zelo raznolika. In ugotovili so tudi, da je njegova poroznost zelo podobna tisti, ki jo ima komet 67P, Churyumov-Gerasimenko. Verjetno se še spomnite tega imena. Verjetno zato, ker so v preteklosti veliko govorili o njem. Namreč leta 2014 ga je obiskala sonda Rosetta in Philae, ki je pristal na njegovem površju. No in ta komet spada v Jupitrovo družino kometov. In ugotovili so, da je Phobos zelo podoben tem kometom in tudi oziroma temu kometu 67P, pa tudi na splošno kometom Jupitrove družine. No in na podlagi tega astronomi sklepajo, da bi ta luna lahko bila komet, ki se je ujel v Marsovo orbito. Oziroma ne samo Phobos, ampak tudi Deimos, lahko bi šlo za dvojni komet, ki se je ujel, oziroma komet, ki je bil eden v obliki približno recimo tako kot je neka pasja kos, dve kugle z neko povezavo vmes in potem sta razpadli, ko sta se ujeli v Marsovo orbito. Tako da to je neka nova možna razlaga. In to je del priprav na leto 2026, ko bodo izstrelili Martian Moons Exploration oziroma MMX, japonske vesoljske agencije JAXA. In ta sonda bo poletela do Marsa in glavni cilj te sonde bo raziskovanje Phobosa. Na Zemljo bo prinesel tudi njegove vzorce in po 3-letnih meritvah in ravno s to misijo poskušali odgovoriti na vprašanje, kako sta Phobos in Deimos nastala in tudi nasplošno, kakšna je bila zgodovina nastajanja našega Osončja. Tako da se že veselimo.
V rubriki Aktualnosti na nebu se bova seveda zaustavili za trenutek na polarnem siju, ki je bil tudi iz naših krajev viden 10. maja. To je bil eden izmed res najmočnejših sijev, ker je bil viden v zadnjih, mislim, da 10 letih ali celo več. In o njem ste seveda zagotovo prebirali v medijih, ker je bila to taka astronomska novica, ki je prišla do marsikoga. Seveda, polarni sij, zakaj je nastal, ne? Zaradi Sonca, to sva po moje že v prejšnjih epizodah omenjali. In mislim, da je lepo, da torej ravno pri tem, ko se osredotočimo na to, kar se dogaja na nebu, ponovno spomnimo, da je Sonce v obdobju aktivnosti, torej najvišje aktivnosti v svojem 11-letnem ciklu. To obdobje oziroma faza najvišje aktivnosti se ne omejuje na mesec ali par dni, ampak gre za fazo, ki traja lahko dlje časa. Torej, mislim, da zdaj v tem trenutku pač najvišja aktivnost nekje predvidevajo, da bo letos in naslednje leto. Tako da se splača še vedno opazovati in preverjati, kaj se dogaja na Soncu. Namreč Pega, ki je v bistvu povzročila polarni sij 10. maja, se zdaj ponovno vrača, torej je ponovno vidna na Sončevi ploskvici in preživela je torej cel obrat okoli Sonca in ker je pač v bistvu ne gre samo za eno pego, ampak za skupino peg, je zelo, zelo možno, in to se je zdaj pred par dnevi tudi zgodilo, da je ponovno imela en močnejši izbruh. In če bo šlo tako naprej, je čisto, torej ni neverjetno, da se bo ponovno prišlo do kakšnega izbruha, ki bi lahko bil usmerjen proti Zemlji in zaradi tega potem povzročil na Zemlji polarni sij. Zdaj, res je tudi, da se trenutno tudi bliža poletje, kar pomeni, da bomo imeli manj ur temnejšega neba, kar pomeni, da bomo morali imeti srečo, da doživimo ponovno polarni sij pač v kasnejših urah ponoči, ne. Ker je seveda je ne bi zaznali, če bi bila ob istih urah, kot je bila 10. maja, ker bo sedaj svetlo še do kasnih ur. No, in še marsikateri drug dogodek bo viden tudi čez poletje, namreč ta trenutna epizoda je zdaj zadnja epizoda te serije četrtega leta temne strani Lune. No, in čez poletje seveda se bo marsikaj dogajalo, marsikateri prizor bo tudi viden na nebu, tako da vas vabiva seveda, da sežete mogoče po knjigi Glej k zvezde, ki jo lahko kupite na spletni strani astronomske revije Spika, ali pa po obilici aplikacij, ki vam tudi omogočajo, da sproti preverjate, kaj je vidnega na nebu. No, eden izmed klasičnih prizorov je seveda meteorski roj Perseidov, ki nastane zaradi tega, ker se Zemlja ponovno prečka, torej sled, ki jo je za sabo pustil periodični komet 109P Swift-Tuttle, ki se v bližino Sonca sicer vrača vsakih 135 let, ampak za sabo pa pušča sled prašnih delcev. In ko Zemlja prileti oziroma se na svoji orbiti prečka orbito tega kometa, naletimo torej na ta meteorski roj. In višek meteorskega roja Perseidov naj bi bil iz ponedeljka 12. na torek 13. avgusta. Tako da v zapiske potem dodajava še vse ostale aplikacije in tudi prelete mednarodne vesoljske postaje, ki jo seveda lahko vedno spremljate. Glasbeni uvod in zaključek epizode je ustvaril Peli iz sosednjega podcasta Opravičujemo se za vse nevšečnosti. To je podcast o življenju, vesolju in sploh vsem.
Kdor želi, lahko z nama stopi v stik preko e-maila podcast.temnastranlune@gmail.com ali pa na družbenih omrežjih, kjer naj najdete z uporabniškim imenom Temna stran Lune.
Z vami sva bili Dunja
in Maruša. In s tem zaključujeva že 4. sezono podcasta. Ponovno se slišimo po počitnicah.
Srečno!
Adijo!